Hello, my name is Rudy Garcia, and this is
Reginald Smith.
And welcome to the Midi Controller drum machine.
MIDI, or Musical Instrument Digital Interface, has been the industry standard for music production since its inception in 1982. Our project is essentially a MIDI drum controller. It uses 3 buttons, and then once you hit the 4th shift button, it can play additional notes. So you start off with 1, 2, 3. If you hold the shift button, you have 4, 5, 6. But that right there is kind of jumping ahead. So let's get into the actual design of the project and how it works. So we can come over here and get a shot of the breadboard. Alright, we're using a PIC16F877A for the microcontroller of this project. The microcontroller is what detects the button presses and inputs. It's what's able to detect the shift button being pressed, and then it's sent over a TX line, which also stands for transmit. That TX line is being controlled by a piece of hardware inside this microcontroller called the AU-SART. AU-SART stands for Addressable, Universal, Synchronous, Asynchronous, Receive, Transmitter. And there are other ways of sending out serial signals to cooperate with MIDI, but having that hardware chip on there is what speeds up the process. There still is some latency on it, and as you'll see later on, when you press the button, there's like a slight delay in the software when it actually registers, but that's only for the recording of it. When it's actually being played back, it would do it at full speed. Alright, now I know we gave a project overview, or design overview, as you may call it, about the overall workings of this MIDI controller, but what I'm going to do now is basically talk to you about how the code works. Essentially, when the MIDI controller is first powered on by a 12 volts DC adapter, it starts initializing itself. The very first thing that initializes is going to be the port interface. The port interface is basically what's telling the MIDI controller what input you want as an input and what output you want as the output. We're using port B for our inputs. Port C is used for the output, and that's going to be for the transmit line, which of course is tied into the MIDI cable itself. Now, once that input and output, or I/O, is set up, the next thing it's going to do is establish the variables that we've used in this program. There are certain variables that are used to keep place. One of those variables are the actual notes that are played from this program. The drum 1 sound has been set up with a note value, and so has the 2, 3, 4, 5, and 6. Now, once that has been established, the program then starts moving into another initialization, which is initializing that AU-SART hardware devices on board the ship that I mentioned earlier. That has been set up to transmit at a baud rate of 31,250. That is the MIDI standard that the serial transmission must operate at. So I established that in the setup of the AU-SART. The next thing the program does is essentially goes into an endless loop. It's a constant cycle, or as you might want to call it, a scanning of the button presses. So as long as there's a button that's not pressed, it continues scanning over and over and over and over again. As soon as a button is pressed, it breaks out into a logical operation. Basically, when you push the button, the program knows that, oh, I have a detection on this input line. It then jumps down to another part of the program where it detects if that button is held. Because with MIDI, when you hold a button down, you don't want it to keep constantly sending a note over and over again. You want it to just be pressed once and it sends out the sound, and until you release it and press it again, it sends out the next sound. So after that button is initially pressed, the very next thing that it will do is see if that button was already held down. If it was not held down, it basically moves to the next part of the program where it sends it out. Once that button is released, I should say, it then goes back to the scanning method. Now, because there's 3 buttons, if button 1 was pressed and it sends a message out, it's not going to start over again at the very top of it. It's going to start over at button 2. That's so that due to the speed of the MIDI, if you want to press 2 buttons at once, so it's kind of send it out at once. Technically in the program, it's not being sent out at the same time, but the musical program can interpret it as 2 button presses based on the speed of the transmission. Okay. Alright, now the last thing I talked about was the cycling of the buttons. After a button is released, the very next thing it's going to do is go down to the button below it. So if you push the button 1, once that message is sent out, it's going to jump down to button 2. How the MIDI controller knows that a button is held and to not send it out again has been established by using the Z flag. The Z flag is a status bit inside of the assembly language. It actually exists in C as well too, but it's just used a little bit differently. Now the Z flag stands for the 0 flag. If it's set, it means that there's a value of 0 at that memory location. So the way to unset it or to remove the Z flag is simply to put a value in there. To keep things simple, we use in our code just a value of 1. So the program's cycling along, nothing's being held. As soon as a button is pressed, say button number 2, it puts a value of 1 at a specified memory location. Now we use the variable depress with a number after it. So since button 2 was pressed, depressed is going to then have a variable or a value of 1 inserted into its memory location. So as soon as that's set, it clears out the Z flag or the 0 bit. So at that point, the program is transferring around. It's transferring out that data over the serial cable using the USART. And when the button comes back around again, at the very top of the program, it's going to say that, oh, this button is held, so I need to send it out again. But once it gets down to that transmit phase, the program is going to detect that, oh, there isn't a Z flag here. So if there's not a Z flag here, it means the button is held down. Once you release it, it jumps down via a go-to operation to clear out the that value of 1. And as soon as the value of 1 is released out of the memory location, a value of 0 is inserted back into it. Once that value of 0 is in there, the Z flag is now set. Now the Z flag is now set. If I was to press that button again, it would then release it out. So what I just described was the reason why, or I wouldn't say the reason why, but the way we coded our program to detect if a button is held, to not keep sending the serial code out like a machine gun, but send it out, and so forth.
Let's take another look at the hardware design of the MIDI controller. The input buttons are Sanwa arcade buttons. These are the same buttons used in many arcade game cabinets. The choice for these buttons were for the durability and sensibility of a button press. Next, let's take a closer look at the input from the buttons into the PIC16F877A port B. Pull-down resistors were used to pretty much avoid the floating pin. Floating pins are susceptible to environmental changes such as static. The 10K pull-down resistors pull the input logic down to a value of 0. Once the voltage of 5 volts is applied by pressing the Sanwa push button, the input logic on the circuit changes to high or value 0.
Alright, what I'm about to demonstrate right now is the actual MIDI controller function. As you can see over here on the board, we have our 3 buttons and we have the shift function. So again, it's going to do buttons, drum presses 1, 2, and 3. And once the shift button is held, it's going to switch up to 4, 5, and 6. It feeds into our actual breadboard, and over here you can see the pull-down resistors that we have set up. And then you can also see the MIDI cable that we spliced into, and that feeds into the actual interface, and it's going to the MIDI input port. Most computers these days don't have they don't have internal MIDI cards, so they devise these external cards. It basically can convert a MIDI signal into a USB. It also does other things such as guitar line in and mic in, but we're really only going to focus on the MIDI input today. So I'm going to go ahead and demonstrate it right now. And as you can see, we have something called Melodic Production M Drummer. It's a free program, at least the small version is. And it's basically, you have a drum pad set up, and you can use it to record samples of your drum loops, which you can then export to any digital audio workstation, so that you can have your bass line and you can actually play your live instruments. So I'm going to demonstrate that right now. We're going to start on 3. 1, 2, 3. Alright, what we just demonstrated right there was the basic functionality of it. We're not going to get into making a bunch of fantastic beats. I'm not sure if I really have the gifted talent for that, but I just wanted to show you that the function of the MIDI controller and how it works.
The inspiration for our senior design project came from my 6 years of music production experience. The use of a MIDI controller throughout most of those years has made production much easier. It enabled me to pretty much control everything within the software I use called Ableton Live. From the control over the octave, pitch, and volume to the sounds I want to use within the software, MIDI has made it possible. Because I am not that great with writing code and assembly, I proposed the idea to a colleague of mine who I knew would be well versed with assembly. Reginald was very enthusiastic about the proposition and was willing to implement his wireless idea to my MIDI idea. Unfortunately, the wireless function was not able to work. We underestimated the difficulty in linking the 2.4 gigahertz RF wireless module to another module. The transmitted signal would then be received by another module, which would then be interpreted by another microcontroller to be sent via serial communication into the computer.
Alright, so we're concluding our video now. I mean, it's been a very challenging semester. Truthfully, time management could have been a little bit better, and I will admit to that. But we have completed it, so we're surprised it worked. I mean, the wireless part didn't really turn out as expected, but everything else did, so we're kind of happy about that. It's been kind of challenging. I would say we both learned more about assembly language.
Especially me.
It seems like when we were actually in 320, 325, and me for 470, because I took the next class up, it was kind of like, oh, what am I doing this for? Why are we doing things this way? But when we were set off on our own, it seems like everything I learned in this class came into play. It came into play or fruition, and things that I was kind of questioning, why are we doing it this way, it actually helped out with the design of the project.
Yeah, I totally agree with him. If I took 470 like he did, I'd probably have a greater understanding of the assembly language, but you know, I'm glad he became my partner, and I'm glad he welcomed his idea with open arms, and you know, like, accepted my proposition. That's, you know, something I owe you for, but definitely just a total learning experience. Like, I learned so much with assembly. Every day we were coding, I was always next to him and by his side, making sure, you know, he explained it to me and we would run through it every time, and it was perfect. Like, I grasped a lot of knowledge from just those sit downs. And building part, like the design of it, it definitely, you know, that's something, you know, you should have known. If you're an engineer, especially like engineering technology, building is already built in there. You definitely have to know that. But, you know, we just did a great time all together, like all around, good work, pretty much.
And I would say, like, what definitely made it out as far as like the whole like testing phase was when we're actually coding it, debugging it. I learned more about how to debug the code line by line, basically setting up like virtual inputs, making sure that when a virtual input was pressed, like the different values are loaded into the different memory locations or registers on the MPLAB program. That definitely helped out with just ensuring that this was going to work and turn out okay.
Yeah, that's pretty much
it.
Yeah.